Okay, class. So at first I didn't grade your test yet. I will do that over the weekend. So you may get some email over the weekend, some weird hour maybe. So, but the good thing is you don't have any quiz or anything over the weekend. Okay, so today we will start the second module of this course, which is pumps. And you can see there are lots of similarities between pipe flow and pumps here. And since this is the very first class of pumps, obviously we need to know some terms and some new terms, something like that. So that's what we will do. And if we get time at the end, we will do some practice problem. If not, that's fine. But just bear with me because these will be lots of talks and everything, but we will watch some videos also, like 1 minute videos. So hopefully the whole lecture will be not that much talk and everything, something like that. Okay, so what is the main purpose of pump? What do you think? Why do we use pumps in any flow system? What does any pump do? They can push water uphill. Okay, so that simply tells you that it is adding some energy to the system, right? Okay, yeah, that is the main purpose of pump. And if you can remember about the energy equation, you remember we always added the pump head and we deducted the turbine head. That's because pump actually adds the energy to the system and turbine takes away the energy from the system. We will discuss that today. So basically, the main purpose of pump is it adds kinetic energy to the system. Okay, it also increases, like kinetic energy means obviously which is related to the velocity. That means it increases the velocity, ensures flow to all parts of the system. It also increases the storage capacity of the distribution system, and it allows for the backup storage. Okay. Now, if you can look at this schematic diagram, this is just an example diagram for water utility. So you're seeing the pump is being used to get water from any surface water storage, like from any river or something like that. Then from there, it is pumped to a water treatment facilities. And from that treatment facilities, it is going to the water distribution. And for any reason, if gravity system doesn't work, the pump will be again used to distribute water into different household or different industry, something like that. Now, I chose this example because we will deal with water in this course, but do you think pump can be used only for water or it can be used for other liquids also? Any kind of fluids, you can use the pump, and there are different types of pumps for low viscosity fluids like water, for high viscosity of fluid like paint or something like that. So we'll discuss that. Basically, those are the things we will discuss for today's lesson. Just a brief introduction to the uses and the characteristics of the pumps, okay? Now, as I said, pump and turbine, obviously pump provides energy to the system and turbine takes away energy from the system. Now, can you tell me, in any hydroelectric power plant, what is the main principle for any hydroelectric power plant? Like, what is the main principle they use?
Like the water falls off the waterfall, and as it goes down, it pushes the turbine and it spins and it makes like electricity.
And that electricity is going somewhere else, right? So if you can think about that part, it's like water system, that is actually the source of energy, right? And the turbine, that is actually taking energy from that source to give somewhere else. Now, if I want to draw a flow chart, it will be kind of like that. For pumps, they use motor or they use the electric energy or mechanical energy to get that flow energy. On the other hand, the turbine, they use the flow energy as a source, and using the generator, they provide the electric power to the other things. So in pumps, flow energy is the output, but for turbine, flow energy is the input. So that based on just the direction or the input-output thing, that is the main difference between pumps and turbines, okay? Okay. Now, what are the common uses of pumps you can think of? Obviously, one is pumping water in gas pump. Okay, what else? Okay, so what is the main purpose of that basement pump? From the basement. Okay, it's like dewater. Sometimes they can use for the dewatering purpose, right? Okay, like some pump, they can dewater the basement or excess water if you have in front of your house or something like that. Other uses, like one of the common uses is in like wastewater and water treatment plant. Obviously, the hydroelectric one, water supply, dewatering. Another one can be firefighting. All of these are related to water, and I chose this example intentionally because we are dealing with water here. But obviously, you know, the pump can be used for food mixing, delivering paint from one point to another point, something like that. But these are just few uses we know from our everyday life, right? Is there anyone who is firefighter here? Oh, great. Do you have anything to say about the firefighting? Like, do you use, like, do you have to maintain the pressure of the water? Okay. Do you get any training? Like, oh, great. Yeah, so we have one firefighter here who uses this type of system weekly basis or monthly basis or something like that. Like how often you need, whenever someone needs you? Okay. So do you work with like Lexington Fire Department? Okay, great. Okay, so let's get back to this class. So these are just few uses where, and do you have anything to say about the uses of pumps for your activities? Okay, but you use some pumps from delivering water from one point to another point. Okay, great. So these are just few uses of the pumps. Now, obviously, we can't use the same type of pumps in every example here, right? There can be differences in pumps. So what we will do, oh, and one thing here is the Bath County Pump Storage Hydroelectric Power Plant. We used to go there for a field trip till 2019. In 2020, COVID happened, and from that time, we don't go there, but it's a huge facility there. And this is the largest pumped storage hydroelectric power plant. Like they have two reservoirs. From one reservoir to another, water comes, and during night, from lower reservoir, they pump the water on the upper reservoir. And that's why it's a pumped storage hydroelectric power plant. And the amount of electricity they produce in one single day, that is enough for whole Lexington City for 1 month. They just produce that amount of electricity in one single day. It's a very good facility. I hope we will start that again. It was good. So it's just 1.5 hours from here. It's near the border of West Virginia, I guess. Yeah. So that is, obviously they use huge pumps there. Okay. Like here, pump generator. So based on the types and how their working principle, we can have two different types of pump system. One is the dynamic pumps and one is the positive displacement pumps. Now, you may heard of the centrifugal pump a lot, right? So that's what we usually use for our water distribution or water treatment purpose. And that is under the dynamic pumps. And before I go into too much details, let's watch few short videos so that you can get a better understanding of that. Okay. Those who are in Zoom, can you see the screen or not? You can? Okay. Because I'm not seeing the border here, so. Okay. So in this video, whatever they're saying about the centrifugal pump, that is actually for the dynamic pump, like the broad category. Let's watch this.
Because a centrifugal pump is a pressure creating device. In other words, as the pressure goes up, flow goes down. It's a direct correlation. Whereas a positive displacement pump, the flow always stays constant. The only thing that's going to change with the flow or performance on a positive displacement pump is going to be the RPM. In other words, each specific cavity.
What is RPM? Rotation per minute, which is the speed of the pump propeller, right?
Each rotation of the pump is going to produce a specific flow. For example, if you had a gear pump, how that fluid flows into the gear is going to determine the viscosity and so forth. However, on the discharge side, the flow is always going to stay constant. So it is a flow creating device versus a pressure creating device. As far as the centrifugal goes, that is the most popular unit ever manufactured in the world. There's about 63% of all rotating equipment in the world are pumps. And within that, probably 90% of them are all centrifugals. Everything from vertical turbines to anti-process. It could be a commercial application. There is an inordinate amount of centrifugal pumps out there. Manufacturer-wise, it's as inordinate as the types. You have everybody from Gould, Durco, Peerless, Summit, Grundfos, and they each have their each individual niche in each market.
Okay, so what he's basically saying, that dynamic pump or centrifugal pump, that is basically pressure creating device. On the other hand, the positive displacement pump, that is actually the discharge creating device. Now, for our purpose, since till now we work with pipe flow and everything, and you know pressure is very important for pipe flow, right? And for open channel flows also. And that's why most of our purpose we can fulfill by the centrifugal pump. Now, to know more about each type of pumps, let's watch a few more videos. Those are obviously short, but you will know the basic.
A centrifugal pump consists of a rotating impeller mounted on a shaft inside a stationary casing. An electric motor or some other driver is used to rotate the impeller at a high speed. As the impeller rotates, centrifugal force pushes liquid outward from the center, or eye, of the impeller. This increases the liquid velocity and creates a low pressure zone at the eye of the impeller, which allows more.
Okay, just to explain this one thing, since the velocity is increasing, that means the more flow is going, like passing with high velocity, that means the flow is not stacking up, right? And if water is not stacking up, obviously the pressure will be less also. That's what they're saying. With high velocity, the pressure is low here.
Liquid to flow into the pump through the suction inlet. Vanes on the impeller help direct the liquid to the outer edge of the impeller and into a gradually expanding channel called the volute, which collects the liquid and directs it to the discharge port.
Okay, and let's know a little bit about the positive displacement pump.
Hello, I'm Amos from Global Pumps, and today I'll be going over what a positive displacement pump is. A positive displacement pump is a pump that traps a fixed amount of liquid and transfers it from the suction side of the pump to the discharge. So what we have here is a rotary positive displacement pump. We have a rotor with pressing shoes that press against the hose, and it transfers the liquid from the suction side to the discharge side. Another rotary style positive displacement pump is this lobe pump. So you've got two lobes which create a cavity and it transfers
cavity means the vacuum
through to the discharge. So it will separate the liquid here, go around here and out the discharge. So what we've got here on the screen is a reciprocating positive displacement pump. So as you can see, it's pulling this shaft backwards and forwards, and you've got a valve at the bottom and another valve at the top, and as it pulls back, it draws the liquid in, and then when it pushes the liquid to the discharge. Thank you for watching, and if you want...
Okay, so from the name, that positive displacement pump, it's just using shaft, they make a vacuum there and liquid actually replaced that vacuum. And that's why it's called a positive displacement pump. And usually this pump, they are used for high viscosity fluid like paint or any food stuff, something like that. But for our purpose, for low viscosity thing, for water or something like that, we usually use the dynamic pump, okay? And that's why for rest of the part of this course, like in which part we will cover the pumps, we will discuss everything about the centrifugal pumps, okay? So we will not discuss anything positive displacement pump other than these characteristics. Most of the discussion will be based on the centrifugal pump. Also, in centrifugal pumps, we will not discuss the design that is for like, we will not discuss the mechanical design, but rather we will discuss the hydraulic design, like we will discuss the hydraulic characteristics of the pump, like how can we select the best pump for our purpose or something like that, okay? So in your copy, there are some blank spaces. Make sure you write down the notes on your copy, okay? Now, since we will work with the centrifugal pump, we need to know how can we characterize the centrifugal pump, or what are the performance characteristics we need to look at when we discuss about the centrifugal pump. So that's what we will do in our next section. There are few performance parameters we need to know for centrifugal pump. So those who are on Zoom, you can see the screen on your computer, right? Okay. And you could see all the videos also in your screen, okay. Okay, so we already saw these videos. Now, the centrifugal pumps, obviously we know that it converts, by now we know that it converts the mechanical energy into the flow energy, right? It takes the energy from the motor through electricity, and it converts that into flow energy. And obviously we can't use the same pumps for treatment plant, for the firefighting. There will be some variation also, right? Based on that, the price varies also. These are just a screenshot I took from the Google, and you can see it can range from 77 to 15,000 or more than that maybe. So these are just few things like to keep in mind, that the price and power and performance of centrifugal pumps, that can be varied. Now, how can you assess the characteristics of this pump? Like when it will be like high price pump, obviously they have something, that's why you are paying high price, right? So obviously that is the performance of that pump, which is like in very high. So how can you work on that part? To do that, we have some parameters for the pump performance, and those are, the first one is rotational speed, which we use N. The next one is discharge capacity. The next one is pumping head. Do you remember in energy equation, we used a term H pump, like for pump head. This is the same thing, like pumping head, that is actually the same thing. And another one is power applied and the efficiency N, okay? Sorry, it's not N, it should be ETA, ETA. So that is the notation we usually use for the efficiency. Now, for efficiency, what should be the unit? Or is it unitless? It's a unitless, or sometimes we express that in percentage, right? What should be the unit for power? What is the most common unit for power when you buy a car or use horsepower? Yes, so horsepower is one of the most common, widely used unit for power, but obviously that is not the standard one, but we will see that we use that a lot. Another standard one can be the watt, right? For bulb or something like that, like light bulb, we usually, we will use 60 watt bulb, something like that. So that is the power. What is the unit for pumping head? Feet, it can be meter, it can be inch, it can be millimeter, centimeter, anything which can be used for the length. That is the unit for pumping head. What is the unit for discharge capacity? CFS, okay. There is another common unit. Wait a few per second, another one. GPM. GPM is the one we use like widely, but obviously that is again not the standard one, but we can convert that to a standard one, right? Okay, for the rotational speed, what will be the unit? It's like speed, how many times? It's a rotational one, so meter per second is a unit for speed, obviously, but that is for the linear speed. For rotational one, you need to count how many rotation it can do within a minute or within a second. You are almost right, yes. So RPM, which is the rotation per minute, again, that is not the standard one. So RPS is the standard one, but we use RPM a lot, okay? Can you write down these on side of each one, that what are the usual units? Okay. Okay, now obviously dealing with 5 parameters, that is kind of difficult, right? To, like for each pump, if you need to deal with 5 different parameters, it's a little bit difficult. So how about we combine some and come up with a common parameter? That's what we did. There is a parameter called specific speed. It's not speed. It's not the rotational speed. It's the specific speed, which is kind of, do you remember the Reynolds number? What is the purpose of Reynolds number? And like what, like in usually what purpose we use the Reynolds number? To know the laminar flow and the turbulent flow, right? It's like we are classifying the flow type. So this is something like that, the specific speed. We use that for classifying the pumps, okay? And they have 2 different expressions. One is the dimensional one, and one is the dimensionless. But both of them has one. N is for what? This N. What is Q stands for? And H? The head, right? So out of these 5, we are combining NQH into one parameter, which is called the specific speed, that reduces 3 parameters, right? Okay, now what is dimensional number and what is non-dimensional? non-dimensional number. What is the beauty of dimensionless or non-dimensional number? It can be used for any unit system. You see here, rotational speed, I didn't write down any unit. Discharge capacity, I didn't write down any unit. Total head, if I use SI system, I will use meter cube per second and RPS. If I use FPS system, I will use feet cube per second and feet. But here, are you seeing for rotational speed, what should be the unit? RPM. What should be the unit for discharge capacity? You can see the screen, right? What will be the unit for Q? What will be the unit for head? That means you have some limitation, like you need to convert everything into these, then you can get the dimensional one, right? Now, the interesting thing, in US, we use the dimensional one, but we act like the number is dimensionless, but it's not true. It's not dimensionless. It's actually dimensional, but we use that as a dimensionless number. So if you want to make that truly dimensionless, you need to add one extra parameter, which is what?
Gravity.
The gravity. If you just use gravity, you can make it non-dimensional number. Okay, so based on this specific speed, we can actually classify the centrifugal pump into different types of pumps, and you can see for each one, they have a limit for, like, either some pumps are good for pressure, some pumps are good for flow, and they have some specific application. Like the axial flow, usually that deals with huge amount of flow, and that's why this pump can be used for flood dewatering or irrigation application. For the radial flow, we don't need that much flow. The flow is very small, but the pressure is high. So usually that is used for the centrifugal cooling fan. And the mixed flow pump, from the name, you can imagine it will be the mixture of what? Mixture of what? Why it's called mixed flow? Mixture of radial flow and centrifugal is the pump, and you can classify the centrifugal pumps into 3 different categories. One is radial, one is axial, and the mixed one will be the mixture of both, right? Okay, and we will watch a video, short video again, just to know more about that. But before doing that, we will see some pictures also. As I said, this is the very first class of pump, so it's just too much. It's just discussion about different parameters and everything. If you participate a little bit, it will make this class less boring. So answer something when I ask something, okay? Okay, so obviously for irrigation application, you need huge amount of water. Whenever you have a flood, you need to dewater the pump. So that time you can actually use the axial flow pump, okay? So for the centrifugal axial flow pump, you can see the pump is rotating this way. The propeller flow is going this way, okay? For the radial flow, this is going this, oh, you are not done. Sorry. Okay. And this is the mixed flow pipe, which can cover a good range of pressure and pumps. Okay. So let's watch a short video again, and we will be done with the videos.
One way that centrifugal pumps can be categorized
is by the way liquid flows through them. Three common flow path classifications are radial flow, axial flow, and mixed flow. In centrifugal pumps that have a radial flow design, the impeller causes the liquid to make a 90-degree turn and flow outward, or radially, from the suction eye to the tips of the vanes. A radial flow pump takes advantage of the maximum amount of centrifugal force that the impeller develops. Generally, radial flow pumps are capable of higher discharge pressures, but they don't move as much.
It says that discharge pressure, not the discharge, okay? This is actually high pressure.
Much liquid as other types of centrifugal pumps. In centrifugal pumps that have an axial flow design, the impeller moves the liquid through the pump along a path that's parallel to the pump shaft. In this type of pump, the liquid is moved mainly by the propeller action of the impeller's vanes. This impeller uses only a small amount of centrifugal force to move the liquid. As a result, the discharge pressure of an axial flow pump tends to be lower than that of a radial flow pump. However, an axial flow pump may be able to move large quantities of liquid. Mixed flow pumps combine the characteristics of radial flow pumps and axial flow pumps. They use centrifugal force and the propeller action of the impeller's vanes to move the processed liquid. For that reason, a mixed flow pump can develop a relatively high discharge pressure and still move a large quantity of liquid.
Okay. So the important information to take from this video is if you need high pressure, radial flow pump is the one. If you need high volume of water or like you need to deal with high discharge, axial flow is the one. But a mixed flow, it can work with a good range of flow and pressure. So if you need high pressure and high volume of water, you can use the mixed flow pump, okay? Now, what is the main parameter based on that we are classifying these pumps?
Like the shape of how the things are, so it flows and makes the water basically.
Yes, that is one way. Another thing is when you don't have the visual, like you can't see that, is there any way, just like the Reynolds number, like we know when the Reynolds number is below 2300, it's the laminar flow. Is there any indicator for these pumps, like without seeing the actual pump, just seeing some numbers, can we identify the pumps? Is there any parameter? Yes. Just look at the second column of the table you are seeing. What is you are seeing here? The second specific speed. Yes. So specific speed is kind of acting like a Reynolds number here, which will give you some idea without the visual. Like just by seeing the specific speed, you will be able to tell, okay, what type of pumps you are dealing with. Okay. And for specific speed, when it's 5 to 3,500, that means like if you do the calculation, you will see it is not providing you high discharge, but it will provide you high pressure. Okay. And one more thing to note, this is capital NS, right? Can you tell me from your notes, capital NS, it's the dimensional one or the dimensionless specific speed? Which one? It's a dimensional one. But you see, I didn't write down any unit. Just what I said, in US, we use this number just like a non-dimensional one, but you already know that is not the true one, right? Okay, so once we know that, we will discuss a little bit about the specific speed. There's a thing called geometrically similar pumps. Now, that is exactly same concept as geometrically similar triangle. Do you remember using geometrically similar triangles? What was the concept or principle of geometrically similar triangles? Suppose you have two triangles and you are saying those are geometrically similar triangles. What does that mean?
They have the same length angles.
They have the same angles, and at the same time, they have some sort of ratio in between the arms, right? The same thing here, the geometrically similar design, instead of angle, they have the same specific speed, and instead of arm ratios, they have the ratio for diameter for different pumps, okay? We will discuss a little bit more about the geometrically similar design, and the efficiency starts dropping drastically when lowering the specific speed below 1,000 because the loss is too much there. High specific speed also have a lower efficiency than the medium specific range. At all specific speeds, smaller pump capacities have lower efficiencies than the pump with the higher capacities. It's just like if you have a small setup of pipes and you have too many stuffs like valves, bends, everything, obviously you will have too much losses, right? So it's kind of same thing here. So smaller pump capacities have lower efficiencies than the pumps with the higher capacities, okay? Now we have two more things before we move to something new. As I said, the geometrically similar pumps, when I say geometrically similar pumps, how many pumps we are talking about? What is the lowest number? At least two, right? So you should have at least two pumps. One is called model, one is called prototype, right? Now, how can you replicate results from model to prototype? You need to know some relationship. So these are just the relationship between discharge, pump speed, and the diameter. And all of these laws are called affinity laws. How many of you already did the pump lab for water resource, like for CE 306? I know some of you are doing water and some of you are doing the soil labs, right? So those who are doing the water labs, did you do the pump labs, pumps in series, parallels? And do you remember you changed the speed and you drew the pump characteristics curve a little bit? Did you work with two different speeds? Okay, so we'll discuss those here also. So here, 1 and 2, 1 can be prototype, 2 can be model, or vice versa, as long as you keep all the like Q, N, D, the same number for prototype, and Q, N, D, same number for model, you should be fine. So did I give you the equations or you need to write down? Okay, good. And here, I think in your copy, I typed pipe, that should be pump. Okay, geometrically similar pump. Now, here we are dealing with two pumps, but have you ever heard about like variable frequency pump, like you can change the speed or something like that? So there are some pumps which is not like that, those pumps can work with different speeds. And that means if you need to know the characteristics of pumps with different speeds, or if you want to change the diameter, how that will affect the total characteristics, there are another set of relation which is for alterations in the same pump. Now for this one, how many pumps we are dealing with, 1 or 2? Is the alteration in the same pump? Just one, but within one pump, you are changing parameters, right? And these relationships are called performance characteristics, okay? Now, those are the few things I wanted to discuss before I start the actual pump characteristics. Now, I know there are lots of new informations here, but did you get a little bit idea of the pump classification and how can you classify different types of pumps? Okay, now if I ask you some quick questions. For water resources purpose, like anything what we are dealing with water, what type of pump we use, dynamic pump or positive replacement pump? The dynamic pump, because centrifugal is within the dynamic pump. Okay, now how many parameters we need to know the performance of a pump? What are the different parameters? 5, right? One is speed, the next one is discharge, next one head, last 2 power and efficiencies, right? Okay, one more thing, all of these P, those are power here, not the pressure. Here, this P stands for power, okay? Okay, now tell me, do we have, for the specific speed, do we have only the dimensional specific speed expression, or do we have the dimensionless also? For specific speed, how many expressions we have? 2. In US, which one we use? But we act like we are using dimensionless numbers. Okay, good. Okay, and for geometrically similar pumps, how many pumps we are dealing with? 2. One is model, one is prototype. For alterations in the same pumps, how many pumps we are dealing with? 1. Okay, I kind of told you all the questions you will see for your quiz next week. You will have this type of questions there, okay? Okay, so are we good a little bit with this one? We can move forward with some mathematical problems or something like that. Okay, so all of you should have your class example for, I think, 6 and 7. Can anyone read the class example 6 and 7? Just see, sorry, class example 7, not 6 and 7. Okay. 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 What is the next part of this question? Okay. And then you have the centrifugal pump classification, and they are asking you to find the model and prototype. Okay, now tell me, before I start working on anything, how many pumps we are dealing with here? 2. One is model and one is prototype. Okay, now we have lots of data here. So what I will do, I will just write down the data first, and then we will select which one we need to calculate and which one we already know. So the way I give you this, like model and prototype, since for each one we have 5 parameters. So let's write down those first, okay? So for model, you can use subscript 1 or M. For prototype, you can use subscript P or 2. Like, it depends on you, like which one you feel comfortable. I personally like M for model, P for prototype. It's kind of easy to identify. So that's what I will do, okay? Model M and prototype P. So we have, since we need 5 different parameters, so NM, QM, HM, PM, and this one, okay? And since they gave you the diameter, I will write down the diameter also, okay? The same thing here, but this time, maybe prototype, Q, Now, tell me what are the given values or what values we already have. Do we have the rotational speed for the model?
3,600.
3,600, okay. RPM, right? Okay. Do we know the Q for the model or discharge capacity for the model? 3. Yes. Okay, what is the pump head? 125. And the unit is feet, right? I don't know about the power at this point or power input at this point. Or do we know? No, that's what we need to find actually. Okay, what else? Do we know the efficiency of the model pump? 84, good. And do we know the diameter? 7.4, okay. Let's see what do we already know about the prototype. Do we know the rotational speed for the prototype? No. Do we know the discharge? Do we know the pump head? 125, okay. Do we know the power input for the prototype? Nope. Do we know the efficiency of the prototype? 80%. Do we know the diameter of the prototype propeller? It's not directly given, but yeah. So you are right. There is a size ratio which is given. Now for pumps, size means the diameter of the propeller. So it says that size ratio of prototype and model. That means dP over dm is what? 10. From that, can we calculate the dP? We have 7.4 to 10. So what will be the final one? 74 inches, right? Okay. Now here, if you want to convert the unit, that is fine. If you don't convert the unit, you will see you are fine also because all the terms, they are like 1/2, 1/2. It's like the same parameter, so they will cancel each other. Okay. So these are all the given values, and you see there are lots of unknowns. We don't know the PM also, and that is actually the first question you need to answer. Now, how can we calculate the power? Do we have anything here which is related to power? What about the efficiency? How can we calculate the efficiency? Efficiency is what actually? It's the ratio between what? Energy out over energy in, or the power in, power out over power in, right? Okay, so that's what we will use. And from this point, we'll start on Monday. Please bring your class examples 7, 8, and you all have a good weekend. Thank you very much, class.